expressing collective phenomena. And our tradition is to ask organizers of the workshop to identify some of the distinguished participants of the workshop, organizers themselves, to give a talk at our weekly colloquium at Simon Center, SUGP weekly talk. And I'm very pleased to say that Herman Verlinde accepted our invitation. And he's going to talk about black hole horizons and quantum many-body theory.
Okay. Thank you for the invitation. I've been to a few of meetings of this type where indeed there's been interesting developments that are of interest both from the point of view of high energy theorists and condensed matter theorists and interdisciplinary workshops like this one indeed are a good way of exchanging ideas. Again, this is going to be partly a colloquium-style talk, but mostly also essentially a talk that fits in the workshop. Again, my perspective is coming very much from high energy theory and studies of gravity. But over time, I've come to appreciate that many of the insights that come from condensed matter theory could potentially be very important to us. And I hope to make that clear a little bit in this talk. Again, since this is a colloquium, I'll start again with the big picture and something very general and actually somewhat ambitious, perhaps, where indeed, if we're interested in the questions of gravity and of what the fundamental constituents of matter are, you should indeed be asking these kind of questions. We live indeed in this universe with a positive cosmological constant. What is it made up from, and how much stuff is out there? And that how much question, of course, is being quantified by entropy. And typically, for most purposes, of course, we can talk about the stuff that we actually see: atoms, photons, neutrinos, and gravitons. But we have indications based on other arguments, basically coming back to Bekenstein and Hawking and Gibbons, that if you have a space with a horizon, and our own universe is a space with a horizon, then there's another component of the energy, which I can call the dark component because it's to the entropy. I can call it the dark component because it's related to the dark energy. The fact that we have positive cosmological constant. There's this cosmological horizon. You compute the area of it in Planck units. And we kind of believe that this number is a good way of quantifying the number of degrees in the universe. And you notice that this number is much bigger than that number. And it means that most of the stuff that's in the universe is something that we probably don't know what it is. And that already gives you a little bit of a different frame of mind, because most of the theories that we're writing down are based on these objects, whereas probably most of the stuff is something else. And this, of course, reminds you a little bit of what happens in condensed matter theory, where you have certain quasi-particles, maybe that are the things that you see at low energy, but the actual UV physics is based on something else. So there's now then maybe a new language. We call it holographic description because this thing is actually given by, again, the horizon area in Planck units. And we therefore maybe imagine that this quantum many-body system that actually has this big entropy could live on the horizon. But part of the whole point is actually to try to understand, of course, physics in this room. But if we want to do it using the rules of quantum mechanics, we basically have to know what this stuff is made up from. Now, that's too hard of a question to answer, so we always make things easier for ourselves by going to more like a toy model or equally interesting questions, potentially, but where we focus on the physics of black holes rather than our universe. There's a similar kind of entropy associated with that, which is proportional to the area. And moreover, I'm going to again go to, of course, a direction, a development over the last 20 years, where we've gained a lot of insight into the physics of quantum mechanical black holes. Indeed, by this paradigm that I just outlined, that there should be a description, a quantum mechanical description that we call holographic, which is really the underlying microphysical description. and that goes by the name of the ADS-CFT correspondence. The holographic theory lives on the boundary. The ADS space is actually the space in which this black hole lives, but it needs to have negative curvature. So that is what makes it a toy model. The book, we call it, has negative curvature, and effectively it amounts to putting this black hole in the box. But the dictionary is you take your boundary system, which is a known quantum system, you put it at finite temperature, and do this description of the object from another perspective should look like a black hole in some space-time. Now this black hole, again, there's all kinds of things you can do with it. You can throw stuff into it, and it will do all kinds of interesting things which have to do with gravity. And indeed, many of the puzzles that we have about our understanding of gravity have to do with the fact that it seems to lead quickly to paradoxes if we combine quantum mechanics with black holes. And thinking about it in this setting is part of the motivation to try to address those paradoxes. Yes?
Is curvature a parameter in the theory?
Curvature is a parameter in the theory. Indeed, essentially we call it something like the central charge or the total number of degrees of freedom. So there's a similar dictionary as I had before that I could start with a certain number of degrees of freedom. Of course, a CFT is a continuum theory, but nonetheless you can count in some sense how many fields there are, and if that number of fields is very large, which is typically why we do large N physics, then this curvature is small.
And one can sort of do some analytic calculations. Is it possible to do analytic continuation in curvature?
Yes, it is possible to do analytic continuations. And typically what people say is that this is a duality. And that there are, because basically this conformal field theory has to be strongly coupled.
So you get physical world answers from analytic continuations in curvature.
People have tried that. Of course, changing the curvature from negative to positive changes all kinds of signs in the process, because you're changing one sign and the many other signs associated with it. And one of the issues indeed has to do with unitarity. But the main issue is actually that an anti-de Sitter space has a boundary. And it's a special boundary where you can see that things are basically scaling up. Each of these little bats has the same area. So basically the continuum limit sits on the boundary. And the de Sitter space doesn't have that structure. Which is why in this case I can talk about a quantum field theory, whereas in the de Sitter space undoubtedly it will not be a quantum field theory that's associated with it. Okay, anyway, so we want to be able to start, say, maybe with a description of quantum mechanics, but the hard question is how to reconstruct things in the book. And in particular, can we understand gravity in the neighborhood, say, of a black hole? And there have been indeed recent developments that also have been highlighted in this workshop, where people have been talking about effects of this gravity system that can be interpreted on the boundary as chaotic dynamics. And these effects have been identified for a long time ago, actually by my advisor at Hoofd in the 80s. He pointed out that indeed if you throw particles into a black hole, and you also include the effect that Hawking identified, that particles can actually kind of escape from a black hole in a quantum mechanical setting. You can have Hawking radiation. If you take a particle that is escaping a black hole, it will take a long time for the particle to escape, and it sits basically very close to the horizon for a very long time. And in that regime, it's highly sensitive to tiny perturbations. If you perturb the particle by a tiny little bit, its trajectory will get changed. And if it goes slightly into the towards the black hole, its future trajectory could be shifted by an exponentially large amount, or maybe by an infinite amount, because essentially it can go into the horizon, behind the horizon, and never come out. So indeed, there's a sensitive dependence on initial conditions where particles that are coming out are highly sensitive to perturbations coming in. At Hoofd at the time was actually trying to use this kind of phenomenon as a way of describing something that he called the black hole S matrix. He wanted to be able to describe formation and evaporation of black holes, and he wrote down what he called an S-matrix ansatz. Actually, in early 90s with collaborators, I wrote some papers where we actually identified the appropriate place for these kind of effects in the form of what we called, in those days, an exchange algebra. meaning that fields that are acting at a later time, which are the fields that measure the out particles, don't commute with fields that are acting at an earlier time. And indeed, we identified that those commutators, which you can nowadays call non-equal time commutators, are actually exponentially growing. And that they grow indeed with a Lyapunov exponent that's determined by the Hawking temperature of the black hole through this relation, which is nowadays called sort of a maximal chaos. Because indeed, in the modern terminology, this exponential behavior and it can be called Lyapunov behavior of a quantum chaotic system, and we call it the butterfly effect. And indeed, it should be visible from the point of view of the dual quantum system that describes this black hole. Yes?
So if the Hawking temperature of the Planck particle is very, very large, that says there's no chaos at the Planck level.
Right. So the black hole has a Hawking temperature. So it's not the particle itself that has a temperature; it's the black hole that has a temperature. So yeah, correct. And the bigger the black hole, the lower the temperature, the smaller the chaos exponent. So the chaotic behavior indeed gets more.
Well, I have it backwards.
Yeah.
The Planck length, it's fully more chaotic.
Yeah, it gets more chaotic. The redshifts are more dramatic in that case. Right. Again, we wrote down indeed this interaction. You can basically see it as a gravitational interaction where the ingoing particle shifts the outgoing particle by an amount proportional to its momentum. And if you realize that the momentum itself is also obtained by acting with a derivative on a field, you get an algebra that looks like this, where this effect, this gravitational effect, is encoded in some, again, non-commutativity, if you like. And nowadays, indeed, in terms of conformal field theories, we encode this property in terms of what's called out-of-time ordered correlation functions, where basically you're considering the overlap of this left-hand side with the right-hand side, and that's the behavior of the 4-point function, and it becomes out-of-time ordered. For the rest of my talk, it's going to be useful. So people often emphasize the Lyapunov behavior in time, but it's actually useful to think about these interactions also in energy space, not just to think about the time dependence as correlation functions, but to think about it indeed as partial waves, where you also specify the energy of the operator that we're considering. And then, indeed, there's a geometric effect. So this thing here is called the Penrose diagram. You have the black hole with two horizons, with basically the past horizon and the future horizon in this case. And if you send in a particle which affects the trajectory of the outgoing particle, you can also represent that actually as a effect that where the ingoing particle actually shifts the location of the horizon. Those two things are equivalent. These are just coordinate transformations. And since each of these particles carry energy, they change the mass of the black hole. If I start with the mass of a black hole with mass m, if there's a particle coming out, effectively outside of here there's a mass that's different than here. This particle is coming in, again another mass. So I have basically 4 regions in my space-time diagram with 4 different masses. And indeed I have, again, the energy of the particles going in and going out that are fixed. And if you know about geometric optics, if you know how the trajectories of high-frequency particles are being influenced in terms of their location, there's a corresponding frequency-dependent phase factor associated with that. And this is going to be an object that I'm going to be studying later on in my talk, which is another way of encoding this chaotic behavior in terms of frequencies. Again, this thing, I'm calling it the R matrix. It contains essentially this gravitational scattering amplitude. You can think about it as the spectral decomposition of the out-of-time ordered 4-point function. And as I mentioned, it's related to sort of geometric optics. So this was the story before Kitaev entered this discussion. Again, Stafford and Schenker had identified this butterfly effect, and Kitaev indeed recognized that these out-of-time ordered correlation functions were a very important diagnostic. Again, he introduced this modified version of the Sachdev-Ye model, which we now call the Sachdev-Ye-Kitaev model, as basically a microphysical realization of this holographic duality between a quantum many-body system and some gravity theory, which perhaps is string theory or maybe something else. It's some gravity theory in ADS. I'm calling it string theory because although the SYK model is a one-dimensional quantum mechanical system, we believe that there's a two-dimensional system that's dual to it, which has characteristics of containing gravity, but it also has all kinds of other junk, probably, and it's probably some non-local theory similar to string theory. But the reason for why Kitaev believed that there was a relationship between these two systems is because he understood essentially the infrared dynamics of his quantum many-body system in terms of another effective field theory, and there may be microscopic ways of understanding the emergence of chaos, but the most convenient and sort of most obvious way in which the chaotic behavior comes forward is by studying this effective infrared dynamics, which nowadays is called the Schwarzschild quantum mechanics, and I'll talk quite a bit about that quantum mechanical system. And indeed, what I'm going to show is that this quantum mechanical system is essentially equivalent to a two-dimensional theory that you can call quantum gravity in a two-dimensional space. And that indeed then establishes a connection between this many-body system and a two-dimensional space-time, indeed with a black hole solution and with this chaotic behavior. Okay, so that's sort of the introduction. Again, actually, the next 3 slides are also introduction because, for most people in the audience, they have seen this SYK model many times already. But let me still briefly introduce it. So it's a Hamiltonian that depends, or at least, it's a system of n Majorana variables that have these commutation relations. It has a quartic or maybe higher order Hamiltonian in terms of the Majorana variables. But the key point is that the couplings indeed are basically democratic. You can think about them as non-local if you think about these things as being at certain positions. And actually you have to draw certain, 4-point interactions here. And these couplings here are random couplings. So this is indeed a system that has pretty random dynamics, and indeed it turns out to have chaotic dynamics. And Kitaev had a rather direct argument. He had to do quite some more elaborate calculations to really establish it, but there was a physical argument for why this theory indeed behaves in the infrared in the way that would make it a good description of something that has a gravity interpretation. So let me quickly go through those steps. Basically, once you have an interacting Hamiltonian, you can try to solve the Schrödinger equation, or you can do it basically with some, you can call it mean field theory, where indeed, since the number of fermions is taken to be large, there's a set of diagrams that start to dominate, which are called Malonic Diagrams. It turns out that all the other diagrams are basically suppressed at large n. And those diagrams are being generated by a set of recursion formulas, which are the Springer-Dyson equations, where if you look at the 2-point function, for example, it decomposes into irreducible components diagrams or a one-particle irreducible diagrams. And those one-particle irreducible diagrams are obtained essentially by indeed acting with this Hamiltonian. Indeed, these are your 4-point vertices for that Hamiltonian. And essentially by iterating these equations, you would solve that theory. It turns out that if you go to the infrared limit of this theory, effectively these equations truncate somewhat to a set of analytic equations where essentially the self-energy, which is called sigma, and this 2-point function is called g, they satisfy this equation. They're each other's inverse. And then the second equation that I had on the previous slide reduces to this one, where this Q is equal to 4. But the point that Kitaev made was that if you look at the infrared region, that these equations actually have a reparameterization symmetry. It's quantum mechanics, so I only have time. I have nothing else in the game. And the reparameterizations indeed only act on that time variable. Since these equations are basically invariant under the reparameterizations, it means that the reparameterizations are a low energy degree of freedom that you have to effectively treat as some kind of Goldstone mode. It's actually a pseudo Goldstone mode, because it turns out that if you include actually the fact that these Majorana fermions satisfy these commutation relations, this symmetry is actually broken by the UV term in the Lagrangian. And indeed, if you work a little bit harder, which Kitaev at least explained in his talks, but which was done more explicitly in the paper by Maldacena and Stanford, you can actually derive a certain effective action for this infrared mode that's known indeed as this Schwarzschild action. Here I'm writing it down. Typically, people write down this first term, but actually, do you know what? Let me talk about this one here. So this is the Schwarzschild action, where this symbol here is known as the Schwarzschild derivative. If you put the system at finite temperature, you have an additional term over here, but it turns out that you can absorb this term into the first one by doing a certain redefinition of your variable f. So in the end, this is sort of the way of writing down the Schwarzschild quantum mechanics. It's quantum mechanics because, again, it's one-dimensional, and my dynamical variable is this reparameterization. This thing has a beautiful structure. It has, in particular, a symmetry under SL2R transformations, which effectively you can think about as some global version of the one-dimensional conformal group. What I found actually remarkable is that this came out of this sort of more complicated SYK model. This is the infrared theory. It's a one-dimensional quantum mechanical system. It's very symmetric, but never in the literature did anyone ever study this particular quantum mechanical model. As I'll illustrate in a few slides, this thing is essentially a hyperbolic version of the hydrogen atom. It's basically, it has indeed SL2R symmetry. This is an SL2R group. Hydrogen atom has SO3 symmetry. It turns out indeed that the Hamiltonian of this theory indeed is the Casimir of the SL2R symmetry. So solving this theory is almost like solving the hydrogen atom, but it actually has quite a bit more structure. And in particular, it has these hints of quantum chaos. Okay, so here's this. I already said this. It dominates in the infrared, and we can basically solve it. And indeed, I'll explain to you how to do computations in this theory. Yes, yeah.
Usually, when I think about infrared, I think about spatial variation. But
right. In this case, it's
in the whole situation. Can you interpret that?
Yeah. So in this case, it's low energy. Actually, this theory turns out to be quite rich. The original, the SYK, this model with the Majorana fermions. If you go to low energy, this thing indeed turns out to dominate. It's indeed the soft modes of the theory that are sort of slowly moving relative to everything else. It turns out, however, that if you go to even much lower energy, that again you have to basically go back to the Majorana description. So this thing is sort of an effective description that works over a very large range of energies, which are mostly low, but not ultra low. So but it's energies. In this case, I'm only talking about energy and not about wavelengths. Okay, where am I? Okay. Yeah, by the way, the next slide is slightly... yeah.
Can this formula be derived as a gravitational anomaly of some simple two-dimensional theory with a boundary?
I'll get to it. Okay. Thank you. Indeed. Obviously, indeed, people who have thought about two-dimensional conformal field theories or things with gravitational anomalies in two dimensions recognize this Schwarzschild derivative as being an essential component of that story. And we're making use of that. So it turns out that, in a funny way, solving this theory was actually easier by first going to 2 dimensions and then going back to 1 dimensions, for a reason that I'll explain. The next slide I'll go over a bit quickly because it's work basically in progress, where I'm discussing, because one of the hopes in some sense is that by thinking about the question, why does gravity come out of random, or at least certain sufficiently chaotic many-body systems, quantum many-body systems, there should be a universal reason for why that's happening. And the universality of it would have to do with the same type of universality that governs the laws of thermodynamics and hydrodynamics, etc. So there should be a certain thermodynamic or hydrodynamic argument for why this theory comes out of this swatching. So let me just outline a little bit of what we're trying to do here. So when we talk about thermodynamics, you want to have entropy, and actually the first law of thermodynamics, which relates energy and entropy, that's been used as a tool of potentially deriving the laws of gravity from a quantum many-body system. Because if entropy is related to area, energy is, of course, another side of the equation, and area is geometry, the relation between geometry and energy is really what the Einstein equations are about. So the question is there maybe a thermodynamic reasoning that would give rise to this action? I'm pretty sure there is, but we haven't quite been able to find it yet. One of the reasons is that if you talk about entropy in 1 dimensions, often we talk about entanglement entropy, which is an entropy between a subregion and the rest. And this is a 1-dimensional system, so there's no spatial separation. So if there's no spatial separation, then let's just separate in time. Not sure if you can see this. This is red, this is black, this is red. And there's an intermediate interval here, which is a segment in time. And I can ask, well, and this is, I think, makes sense in a theory of a large n limit. It turns out that for a large n theory, if you look at the observables that are confined to a certain time interval, they can actually be shown to commute with observables that are living in another time. And therefore, there's an operator algebra associated with this interval, and you can associate an entropy to that interval. So this is an interesting way of thinking about it, potentially. Another way of looking at it is that, suppose I identify this interval. This is, again, my total time interval, and I want to associate sub-Hilbert space to it. Let's do a coordinate transformation where I introduce a new coordinate, which is the tangent of pi times this coordinate. And then if this coordinate goes between here and there, that new coordinate stretches the whole real line, and the outside of that interval is being mapped on another real line. And now I can sort of put those two real lines next to each other and talk about the spatial entanglement between these two things. That's another way, perhaps, of thinking about this. And then, in that case, this turns out to be the thermal entanglement, basically, of a thing with that temperature. So basically, the length of that interval turns into the temperature of this thermal entanglement. So this is a quantity you could compute in your SYK model. Now, you would put some dynamics in this, and basically put some dynamics in it by throwing in some energy. And this is the part where the question marks show up a little bit. And there's an equation that I know would have to be true based on what I know what this system is dual to, which I would want to call the first law of entanglement thermodynamics, or at least of time entanglement thermodynamics, where there's some notion of energy that I can pump into the system. And then there has to be a relationship between how this entropy changes as a consequence of that energy. And these are equations of motion of a system that I could then integrate. And the proposal is that this should uniquely fix this Schwarzschild action. Anyway, let me go on. So the evidence that has been sort of accumulated in the last year and a half, 2 years, suggests that indeed this SYK model is dual to a two-dimensional gravity system. Here I'm writing down the action. Two-dimensional gravity is a bit special because you cannot write down the Einstein action because that would be a total derivative. You have to introduce a field that multiplies the Einstein term. And if you do it this way, actually this thing effectively acts like a Lagrange multiplier that imposes constant curvature. So the metric of this thing is really just constant negative ADS space-time. But there is this field phi, which actually turns out to be effectively the same type of variable as the area that I talked about earlier. Phi plays the role of area, and it turns out that phi indeed has the interpretation of entropy in the dual system. It turns out that in order to find the relationship properly between the SYK model and dilaton gravity, what you need to do is you need to take ADS2, that's where this place lives, where this theory lives, and you have to take this field phi, and you have to give it a constant value, and actually it turns out to be the value of phi turns out to be generally diverging on the boundary, but you put a cutoff there, and you allow this thing to have a very large value, and then the constant value of phi defines a particular line in your space-time. And if you throw in energy, this line will start to wiggle. But the dynamics of that line turns out to be described exactly by the Schwarzschild theory. There's another way of actually describing the dynamics of that boundary line, which is actually quite beautiful, which is to take this area over here and simply integrate the total area surrounded by the red curve. And it turns out that also that integral is equal to the Schwarzschild action, if you use that as a variational principle. And one way of seeing that is that basically we're integrating the external, how do you call it, extrinsic curvature of that line, and by Gauss-Bonnet, that's equal to the curvature integrated over the area, and the curvature is constant, so basically I'm just integrating the area. And it turns out that that's basically the same thing that you would do if you would put a charged particle on a hyperbolic plane, but in a constant B field. So this actually has some relationship with the Landau problem on the hyperbolic plane. So that gives all kinds of hints of how you might want to go about solving this theory. Okay. So now I'm going to indicate how to solve the theory, and I'll start with just the most basic way of which you would do it. So one of the funny things about this action, if you remember what it looks like, it has higher order derivatives, and the Schwarzschild theory with this higher order derivatives is not usually, doesn't seem to have the form that you would normally recognize as a thing you can quantize. So I'm going to actually claim that there's, I rewrite it. The variable in my Schwarzschild action was this f variable, and it turns out that if I take a field that I call phi, and I require that the field phi is actually the logarithm of f dot, which is what this Lagrange multiplier implies. So phi is the logarithm of f dot, and I just write down phi dot squared. That's the Schwarzschild. Now phi dot squared is nothing else than pi phi squared pi phi phi dot. I can integrate out pi phi. So this thing, indeed, I can easily rewrite it as the Schwarzschild. It's has more fields in it. It has 4 variables. And indeed, the phase space of the Schwarzschild quantum mechanics is naturally 4-dimensional, because it's a higher derivative theory. So now I have my canonical commutation relations. I have my Hamiltonian, and I have I can do the quantum mechanics. This thing has this asymptotic symmetry. The corresponding generators you can just compute using Noether's theorem, and it turns out that this Hamiltonian is indeed the Casimir of the asymptotic symmetry. So that's about it. Essentially, this solves almost the spectrum of the Schwarzschild quantum mechanics. Indeed, basically, it's labeled by asymptotic representations. asymptotic is a non-compact group, so representations can have a complex label, and the energies indeed are labeled then in this way in terms of a continuous variable k. This is not quite the end of the story, because there are many other things you would want to know. You want to know the spectral density of this theory, and you want to know its correlation functions. Yeah.
What is the difference between this problem and the problem of just boundary states in linear dilaton theory?
Boundary states in linear, you mean in the linear dilaton theory? So in this case, Again, it's not literally linear dilaton because it has a slightly different action. It's the Sachdev-Ye-Kitaev theory that we're talking about here. There's the phi r, but there's also the phi times lambda piece. Phi times lambda. So if I go back here, there's this thing here, and that changes the story a little bit. Right. But it's true. There's a relation, and this was also mentioned, between this theory and what you would want to call the boundary dynamics of some 2D theory.
Would also be present if you just had a line in the dilaton theory. There would be some big term. There would be an SL2R.
Yeah. This thing is a boundary of a theory that looks like phi times r. Right. So it's sorry. Yeah, but you can. This R looks like, at least if I go to conformal gauge, like the box on some conformal factor. So the phi has a kinetic term in this way of thinking about it. So this is a quantizable theory. It's part of a more general class of theories, but this is the theory that has the SL2R symmetry and that has naturally the ADS2 underlying.
Maybe this theory, without matter, it has no degrees of freedom.
Right. That's right. But it will get a one-dimensional degree of freedom basically as an edge mode. So it's a bit like it's a 2D version of a quantum Hall type system, or at least where there's nothing in the bulk and everything is happening on the boundary. That's right.
Some degrees of freedom in the bulk, and then the boundary action would be non-local.
That's right.
So the boundary action is local.
Right. If you would have massless fields on the boundary and you would integrate those out, you would get some non-local additional terms. And those non-local additional terms, effectively, actually, they would correspond to what you would call matter. If you go to lowest energy, again, typically the non-local terms do not. Again, you do a derivative expansion, basically. And then the non-local terms do not affect they may renormalize this action, but the infrared effect of action is dominated by the swatching.
Short question.
Yeah.
Is it possible to see equation of motions?
Sorry, which?
Equation of motions? How much action change when we deviate from its minimum?
Yeah, so there are equations of motions, which actually I had on my one of my previous slides, but the equation of motion for the metric doesn't change at all. The metric doesn't backreact to matter, because this thing always stays ADS. This thing has an equation of motion, and the equation of motion of this thing is precisely this first law of thermodynamics that I wrote down earlier, that this thing is actually the entropy, and the way it backreacts to energy is precisely the way entropy would backreact to energy. So, okay, I can write it down. Basically, it's the second derivative, probably some covariant derivative, with so alpha beta on phi is equal to your stress energy density. That's your equation of motion.
And stress energy expressed so phi.
So this is my matter. So there's no. Yeah. So this is the matter. So that's how the bulk would be. Okay. Further questions? Okay. Let me outline how one would go to the partition sum. So there's a nice paper by Stanford and Witten, who just simply pointed out the following. Okay, I have this swatch in action. Let's go back to the original formulation just in terms of one variable f. And I have to do that integral. So this is my functional integral over time. So f is a function of time. And so this is my partition sum. But now let's look at the configuration space of this integral. Meaning, rather than thinking about it as the quantum mechanics, let's actually think about this integral as an integral over some space. And it's the space of the diffeomorphisms of the circle. Because the action has the SL2R symmetry, actually my configuration space over which I'm integrating here is diff S1 over SL2R. For mathematicians, if they see this space, they immediately say, oh, that's a symplectic manifold. It's a symplectic space. there's a natural set of commutation relations that I can associate with this, and there's a natural symmetry algebra associated with this, which is the Virasoro algebra, which is the space of diffeomorphisms. I'll make use of that in a second. Witten and Stanford made use of a somewhat more limited property of this thing, that this thing actually has a U1 symmetry that allowed them to evaluate this integral exactly using a Dijkstrom-Heckman theorem, which nowadays we call localization, and they got an exact expression for the partition sum, and they extracted an exact expression for the spectral density, which turns out to behave like that. So this is the spectral density of the theory. We're going to be interested in correlation functions, so I want to think about it a little bit more. Indeed, the fact that this is a symplectic manifold will help us a little bit. And as what I want to claim is that if I put some kind of symplectic form on this, basically I write this thing as a phase space, and I write down Poisson brackets natural Poisson brackets between the corresponding variables. Then if I group my variables in terms of quantities that I call Ln, just by taking Fourier components of this Schwarzschild derivative, those things will satisfy this algebra, which is known as the Virasoro algebra, and it has a central charge, which is basically related to the h bar of the symplectic form. So the classical limit would actually be c to infinity. Now, if I would quantize this theory, and then I would get a natural space that's called the identity representation of the Virasoro algebra. It's the identity representation because of the SO2R symmetry that keeps the ground state invariant. So basically, I'm now going to tell you that I can do this integral now quite easily once I know that this thing is actually an integral over a phase space. Because consider this integral over a phase space. And I can do that integral in a way that seems more complicated by first actually doing the quantum mechanics of that phase space. And then write down the trace of e to the minus h, and then take the h bar to 0 limit. The idea is that basically you have Planck cells here that are tiling your phase space, and summing over all the Planck cells gives you that integral. And I can do the same thing here, where now that trace can be written as the trace over my the identity representation of my symmetry algebra. I have to take the h bar to 0 limit, which is c to infinity. I have to do it in some combined way where this quantity q, which is anyway, is defined in a particular way. But anyway, if you do this appropriately, you can actually identify this quantity with that partition function, just based on basically a geometric argument. I should tell you this is the favorite way in which I'm doing calculations by not doing any work, basically by identifying at least a geometric structure. One thing to keep in mind, though, again, I need to point out, I started here with an integral where time was going like this. But now by writing down an integral as a trace over some other dimensional Hilbert space, I'm introducing a new time variable to do my quantum mechanics. That new time variable in which I'm doing my quantum mechanics was not my original time. The original time was my diff S1 time, and now there's another direction in which I'm doing a trace. So effectively, this thing indeed is a torus partition sum. But I'm working in the limit where the torus gets very thin. Yeah.
This reminds me of is this thing that they call the coadjoint orbits of the Virasoro.
That's exactly what I'm talking about here.
So, well, you said that nobody studied the system before, but I see works about this thing from the 80s.
Right, but no one had studied the Schwarzschild quantum mechanics before.
Both facts, the relation to quadrant orbits of Schwarzschild action in relation to the character of Virasoro were explained in this audience. The auditorium, the scene first contemplate and then the fold up and
Yeah, I'm completely aware that you know all this stuff. I've explained it to many people too, and I'm going to explain it to you now. But I know you know it. Right. You're going to recognize other things in my slides that you know very well.
Speaking about luminescence, is this related to what's called Mabuchi, right?
related to the... yeah, they're I'm less familiar with. We should follow up on that. Okay, where was I? Anyway, so here's my way of doing this computation. I look up the identity character of zero algebra, I take my limit, and I get a partition sum out of it just by taking the limit. So I don't need to do any integrals, I just need to know what the quantization works for. But now we can do correlation functions. And if anyone would know how to do these correlation functions, now why am I writing down this particular funny object? The reason I'm writing down this particular funny object is that my swatchen has this SL2R symmetry. And it's natural to look at correlation functions of objects that are invariant under the SL2R symmetry. And it turns out that the object that's naturally invariant under the SL2R symmetry, you can think about them as bilocal operators. In the SYK model, they actually correspond indeed to two-point functions of the fermions, or powers of local operators. And then when you evaluate them and express them in terms of the variable f, they take this particular form. For the expert of ADS CFT, these are boundary-to-boundary correlation functions, but on this fluctuating boundary. Boundary-to-boundary propagators. There's a label L, which is the mass of the field in the Bock, or it's the representation of SL2R associated with this bilocal observable. And we want to be able to compute arbitrary correlation functions of this. And as I mentioned, this thing can be thought of as a boundary-to-boundary propagator. And in a moment, I'm going to consider a bunch of them. And I want to start looking at interactions between them. And I'll be able to extract gravitational interactions from how these things interact with each other. I'm going to be writing down my correlation functions not just in position space, as I already indicated. It's going to be useful to actually write them as integrals over momenta, over intermediate energies. And therefore, I'm going to introduce amplitudes that are here, which depend on the intermediate energies. My next slide, I'm going to take a little bit of a jump. I'm going to tell you how to compute these things. Indeed, using the relationships that people are anticipating here, that this is actually a limit of this two-dimensional theory. And the underlying two-dimensional theory here is really Liouville theory. And Liouville theory is a theory whose equations of motion just give you a two-dimensional constant curvature metric, like the ADS2 metric. Oh, what happened here? There should have been a hyperbolic cylinder over here, but it doesn't show up on my projection very much. On my screen, it's here. Okay. So imagine there's some hyperbolic cylinder between the top and the bottom, which is the solution to a constant curvature equation. That's the equation of motion of this theory. If you solve that and you evaluate e to the L phi at that point, you get an expression that if I take the F power of this thing, it's precisely this object whose correlation functions I want to compute. And indeed, because of all the comments that were made earlier, it turns out indeed that if I take c to infinity here, and I compute the correlation function of this object in that theory, in the c to infinity limit, I get the answer for the Schwarzschild theory. This is something that we could show based on indeed the same logic as we had for the partition sum. So an assertion of this thing in the Schwarzschild corresponds to an assertion of that object in the Liouville theory. Yeah, there's the coupling to the curvature, correct. But here I'm doing it, say, in a relative flat space. Correct. So in order to make things more interesting, so I could talk about a two-point function, and we computed it, and we made some very explicit checks of how that two-point function behaves at finite temperature. But the four-point function is the interesting guy, because it's the one that's the diagnostic for the chaos exponent. And then you can do two things. You can have, so I call this a four-point function, but it's actually a two-point function of the O's, because I have two boundary-to-boundary propagators. So in the Schwarzschild, this has four insertions of operators, but I'm contracting the large n indices here. But if I consider this correlation function, this is the boring one, because it's basically just two particles just minding their own business, and literally they mind their own business. Because it turns out that these operators, because they are SL2R invariant, they actually commute with the Hamiltonian. And therefore, they basically completely decouple. But things get much more interesting when you go to out of time order, where basically you start braiding the endpoints of these two-sided operators, and you put them in this order. And this is really where the interesting stuff is happening, because this is really the scattering process that I was describing earlier, close to the black hole horizon. It starts showing up in this out-of-time ordered correlation function. From the point of view of this cylinder, hey, there's a cylinder, the hyperbolic cylinder. The two situations, actually this situation corresponds to that side. This situation corresponds to that side. And in order to go from here to there, indeed, I have to sort of basically braid these endpoints. And from the point of view of this Liouville theory, it means that instead of considering these things as time-like separated, I move them across each other at light cone, and I consider them space-like separated. And in the process of doing that, you actually pick up a discontinuity across the light cone, which for a conformal field theory is indeed given by this braid matrix. So the thing to do would be to compute this matrix, because that's the actual interesting thing. So in the Swatchen, you could easily guess what that thing is. Maybe Nikita knows the answer. Do you know the braid matrix of the Swatchen? You know it. You just don't know the answer yet, but you knew the answer in the past. Okay, I'll remind you again of what you knew in the past. Because I can give you the answer already. It's the exponent of this thing is equal to the volume of a hyperbolic tetrahedron, and it's actually the 6J symbol. That's what this R matrix is, and it's the scattering process that takes place in ADS to gravity. So just to remind people a little bit of what braiding meant for us in the past. So braiding is a property of conformal blocks in conformal field theory, or indeed of particles in a two-dimensional condensed matter system. And famously, at least for Chern-Simons systems or Westermann-Witten theories, conformal field theories, there's a relationship between the wave function of a particle, say in quantum Hall, and conformal blocks in the CFT. And the reason for why that's an interesting relationship is that these conformal blocks, which are the chiral correlation functions of the CFT, so what you have to do, you have to take a CFT and take the square root out of its correlation function and only consider the left movers, say. Then those conformal blocks have multivaluedness, and the multivaluedness is the R matrix. And the claim is that if I take these conformal blocks to be the Virasoro conformal blocks, the blocks of a two-dimensional CFT with large central charge, this R matrix can actually be computed. And it's indeed in the large C limit, the R matrix that we're going to be interested in. If I have time at the very end, I'll tell you how to compute it, and I'll remind Nikita of things that he knew in the past. Indeed, the upshot of it is that we actually know what this matrix is. It's given by some function, which I'm just going to call W, which is known as a Wilson function. It's some linear combinations of 4 F3 hypergeometric functions.
Symbol, and you're taking the classical limit, it should be some kind of volume of the hyperbolic tetrahedron.
Thank you for that question. Okay.
It's more elementary than F43. It should be the logarithms.
No, if it's SL2R, it's actually F43. But the semi-classical limit that you're talking about is a different one that I'm taking here. This is the C to infinity limit. But if I would do the following, if I would take C to infinity in combination with all these quantum numbers to infinity, in combination with C to infinity, that's like a WKB limit. And then you're right, that is the volume of the hyperbolic tetrahedron, which I'll now explain. Because indeed, the relationship between the 2D theory, which is dual to the SYK model, completely models a dimensional reduction of a known correspondence between 2D CFT and gravity in 3 dimensions. Basically, here we go, 2D Virasoro CFT is basically 2-dimensional quantum hyperbolic geometry. And this is for the people that know about conformal field theory in 2 dimensions. This is the stress tensor, typically with a conformal dimension and a now I'm summarizing one of your papers. Thank you. Although this is known since the 80s, that if you take this expression and you postulate commutation relations between that quantity and those poles, the location of the poles here, that commutation relation introduces again a symplectic form. You take this thing and you can actually associate a constant curvature metric to it, and then this thing is actually the natural symplectic form on the space of constant curvature metrics. Now you could ask, what do you get if you quantize the space of constant curvature metrics? Turns out that what you get is basically the conformal blocks of a two-dimensional CFT. And the conformal block that for us is interesting is a conformal block where I take two heavy operators. I should have emphasized that here. If this delta gets too big, there's a certain curvature singularity associated with this. So if this delta is small, the curvature singularity is just one of these elliptic singularities. If the delta gets too big, it looks like this. If I want to create a black hole in a two-dimensional CFT, I create a heavy state, and that black hole will create a geometry that looks like this. It will correspond to a geometry that looks like that. And then what you can do, indeed, is you can compute the effect of essentially what happens when you want to interchange the location of two particles. And when you want to interchange the location of two particles, if I'm interested indeed in these partial waves that I was introducing earlier, namely the energy dependence of the scattering phase, I want to project on a certain energy state here. And then after the particles have passed each other, I want to again project on a certain energy state. But this projection and that projection are not the same. And there's a particular transformation associated with this, which was beautifully computed, at least explained in a paper by Nikita and Samson and collaborators, that if you do this particular computation, indeed with the commutation relations that I wrote in the previous slide, you indeed find that your R matrix is equal to some action of some phase, and that phase indeed is the volume of a tetrahedron. That's right. So, and it turns out that this is precisely the scattering amplitude by this picture, actually, that you would want to compute in the gravity. So this sort of ties things all back together, that at least the gravity and the Schwarzschild, of course, are related because basically they were the same classical system. But now you can actually understand how the out-of-time ordered property is showing up in terms of essentially a natural quantity, which is this R matrix. Yeah, so in this case, you have to take the dimension to infinity and to leading order in large central charge. Then you get this particular answer.
So this action should be somehow the same thing that Malonic works out, right? Malonic has this semi-classical limit for the conformal blocks of large sets.
Right. If you evaluate the Liouville action a la Samolochikov, it's actually the same as evaluating the bulk gravity action, ADS3 gravity action, for the geometry that I had initially. By the way, the fact that this thing looks like a 6J symbol and a tetrahedron, if you recall the diagram that I had very early in my talk, and maybe I'm tempted to, which was basically the Penrose diagram with the particle going like this and the particle going like that, and I had the four things sitting here and those things. If you look at that diagram, it actually is a tetrahedron, if you think about it from a 3D perspective. And the semi-classical action associated with this is that object. Here's a slide that I'm including now because I wasn't including it in my previous talk. So, and then I'm almost there because I think my time is essentially up, or past up. Let me give you a little bit my sort of chaotic, at least the chaos. Where does that enter into all of this? Here, allow me, at least I'm now calling the things A and B. These were my fields, that one perturbation that I'm throwing in, one perturbation that I'm getting out. And the question is, suppose I want to send you a signal and it's going to arrive tomorrow, and that signal is going to be A. But someone else, the butterfly, comes in between now and tomorrow and acts with B. And I'm giving you the state where A and B has acted on my initial state. The signal comes, I'll give you that state. If you expect this message, you will not be able to read message A, because B is in front of it. So now suppose that you say, oh, no big deal. I'm going to interchange B and A and try to extract A by putting it out front. The magic thing about this particular R matrix is that once you want to interchange A and B, it comes that you have to reparameterize. You have to act on this alpha index, and it becomes a beta index. And the chaotic system has the property that once you interchange these operators, that basically the operator B, which now acts first, will actually increase the energy of your initial state by an amount that's bigger than the energy of your final state. And therefore your operator A, whereas here it was increasing energy, you could think about it as a creation operator, it became, here it lowers the energy, and you can think about it as an annihilation operator. And the reason for why it lowers the energy here from the bulk perspective is because this operator is actually sitting behind the horizon. And stuff that sits behind the horizon has negative energy. Its information is completely hidden from you, even in this situation, although it's sitting here out in the open. But it's sitting here out in the open as an operator that acts between a density of states that's bigger here than there. And operators that go from a high entropy to a lower entropy part of your Hilbert space, you cannot really decode them if this is some random state. So this is sort of an information theoretic perhaps way of saying what it means to, or thermalization type interpretation of what it means to go behind the horizon. Do you know what? I think I've used up my time. Thank you.
Good questions.
So earlier in the talk, you were talking about entanglement of the time stretch.
Yep.
What exactly is it that you're computing? Is it volume law in time or area law, or what exactly is the? What are you computing, and what exactly is the?
So in the case of the boundary system, indeed, as I mentioned, what I could do, which is one type of quantity I could look at. So I talked about these bilocal operators, and I could look, for example, at the operator algebra spanned by the bilocal operators that are all fit within this time interval. And that's not a complete algebra of the system, and therefore they can have that there's an entropy associated with that algebra. From the point of view of the bulk, what's going on is that again I just have a two-dimensional ADS space, so there's no such thing as a Ryu-Togenagi surface, because I can Ryu-Togenagi is in a spatial slice, and it's a geodesic or a minimal surface in a spatial slice, and my spatial slice is just a line. So the only way in which I can divide up the bulk into two halves is just to identify a point in the bulk separated from the boundary. And I claim that the quantity that actually measures the entanglement entropy in the bulk from the two sides of the interval is the value of this field phi, which I call the dilaton. So that's the geometric quantity that I'm trying to define from the point of view of the boundary. Actually, through the story, by lifting the story from 2 dimensions to 3 dimensions, there's a longer story you can add to this, but we can do that afterwards. Yes?
If you interpret the Schwarzschild quantum mechanics, is this unitary quantum mechanics?
It is unitary quantum mechanics. It's with a continuous spectrum. It may have the same issues a little bit as that what Liouville theory has, that maybe the ground state is a bit harder to identify.
Has the number of states remain constant in time?
Constant with energy, you mean?
In time. So the time evolution in space at some initial.
Yeah, the number of states remains constant in time in this theory, because the Hamiltonian is the Casimir. So once I know the energy of the state,
So what do you mean by entropy attributed to time interval? You have assigned to time interval.
This thing is a gauge theory. At least from the point of view of the Schwarzschild, for example, that thing does have entropy associated with the time interval, because what I could do is I could restrict myself to the SL2R invariant subspace. So the SL2R invariant subspace of an interval is not, if I have two intervals next to each other, and I take the SL2R invariant subspace of this one, and the SL2R invariant subspace of that one. That's not the same as the SL2R invariant subspace of the combination.
What do you mean by that one? Space of states associated to a point, not to an entropy.
No, the space of states is associated. No, if you want to have an entropy, you can associate it to an operator algebra. So there's a definition of entropy associated with an operator algebra, and I can associate an entropy to an operator algebra of operators that act within a certain time interval.
It's not the log of number of states.
You cannot write it as in terms of the von Neumann entropy, but what you can do is you can take your density matrix and you try to construct a density matrix that fits within your operator algebra, that has the property that all its expectation values are the same as the one of my original actual state. And then you can construct a density matrix, and then indeed it's of that particular density matrix that you can compute the von Neumann entropy. So there's a definition that one could use.
Unfortunately, we do not have time, so I suggest to